an example of a quick opening valve. We were talking a little earlier about standard full-ported ball valves not being great as far as modulating control valves. The reason why? They have a flow characteristic like this. Small percentage opening, and you get a lot of your flow. That's not what you want if you're using modulating type control. So you can see here we're open about 30%, and we've got probably about 90% of our flow. Linear valves, on the other hand, those are typically used in like steam applications. So for a 50% opening, you're going to have 50% of your flow, which sounds good, but if it's being married up to heat, air, and cooling coil, that's not really the kind of valve you want either. This is, like I said, more for a steam type application. 50% open, 50% flow. Equal percentage is what you're going to look at for modulating controlled application of coils. You can see here, this is the equal percentage curve. You may have seen it in the past, may not have. The reason it's called the equal percentage curve is because it's the mirror image of the coil curve. So this is the curve for a heating and cooling coil. The reason we want this equal percentage characteristic is because we want our heating output to be linear. So at 50% of our control signal, we want 50% of our heat output, which doesn't equate to 50% of our flow. Because the coil is really more of a quick opening, we want to balance that out with a slower opening valve. So the full-ported ball valve, it's a modified equal percentage. Like I said, it doesn't do as good a job controlling modulating flow. Three-way is also a modified equal percentage. Globe valves. The two-way bronze, equal percentage. Two-way stainless, equal percentage, with the exception we do have a model that's linear. So that's why the L is in here. GLCS, it is a linear control. And then the two-way stainless threaded is a linear type valve, typically used in steam applications. The three-way globe valves, diverting is a linear application, or a linear characteristic, I should say. Three-way bronze, and these first two are both the NPT. The A port is a modified equal percentage. B port is a modified linear. And then you see the both three-way bronze and stainless flanged are linear valves. So the CCV, combined with ball valve technology with a characterizing disc that's given us that equal percentage characteristic. So we discussed earlier, what is the disc doing for us? That's what it's doing. There's the disc itself.
So your ball is not actually cut into being.
The ball is not cut. We actually use a disc here. Okay. Yeah. One of the benefits of that is that we can put different discs within the same valve. So we can keep a bunch of the same valve body on the shelf, put different discs in for different CVs. And I like this slide from the standpoint that it really shows what that disc is doing for us. And I like looking at the 50% open disc, because you can see here, this blue area is where the water is flowing through. This gray area, you can see the curvature the way it would be. You're only getting about a third of the flow that you would if that were a full-ported ball valve. So it's nice that it gives you that equal percentage characteristic where you're getting lesser flow when you first start opening it, and then you start getting more and more at the further openings. The two-way CCV is an equal percentage valve. Three-way is a modified linear valve. A high temp CCV is an equal percentage with the exception of these three models, which they will have an asterisk in the catalog. The reason those are an exception is that they don't have the characterizing disc. Now, the V-ball, you were asking about the characterization being cut into the ball. With the V-ball, it is. The ball itself has the V cut into it. Okay. This is more of an industrial style actuator. Handles the higher temps, higher pressures. But it is an equal percentage valve with that characteristic cut into the valve ball. Six-way valve is a linear valve. We talked about that earlier. Zone valve, it's a quick opening. Inside, it's similar to a butterfly valve. You know, it's got a little flapper in there, not metal, just a little rubber flapper. So it has that quick opening characteristic you see there. And the three-way is a linear characteristic. Butterfly valve, it's a modified equal percentage. As we talked about earlier, we have a 60-degree CV and a 90-degree CV rated for the butterfly valves. That's why we call it a modified equal percentage. You can get some decent modulated control, but only through about 60 degrees rotation of that disc. Once you're beyond 60, you're not really getting any kind of modulated control. And the three-way is a modified. PICCV. This is as true an equal percentage valve as you're going to find on the market. EPIV, same thing. All pressure independent valves are very much equal percentage. EPIV can be programmed to be linear if need be. If you're using it in a bypass application, you can set this up to be linear through programming of the actuator. Energy valve the same way. It's based on the EPIV, so it can be either equal percentage. It comes from the factory, excuse me, equal percentage, but if you need it to be linear, it can be programmed. So some of the valve limitations. I'm going to sit down. I have to click on some buttons here. Be able to hear. I know there's some volume in some of them. So there's temperature limitations. You know, we don't want to see the actuator melting out there. The actuator, most of our actuators have an ambient limit of 122 degrees. On the cold side, we certainly don't want to end up having ice inside the valve either. That's going to damage the internal components of the valve. Pressure. It would take a lot of pressure to do that to the valve. But if you get enough pressure, it's probably not going to do that, but you're probably going to get little cracks in the valve. But the majority of our CCVs have a 600 PSI, what's called the burst pressure rating. And then some of you may have heard this noise before. I'll just mute it. You know, referred to as water hammer. Just if your velocity is too much through the valve, you can get that noise, because what's happening is you're causing vapor bubbles, and they're bursting inside the valve.